So why are we doing this? Well, climate models are in many ways a great accomplishment of mankind, but they still have some shortcomings in terms of their ability to provide the best possible information to society. And this picture just shows one of those shortcomings or uncertainties that we still have. So this is for the region of the world where I come from, the Pacific Northwestern US. A picture of decade by decade actual temperature, unfortunately in degrees Fahrenheit, change from 1900, and decade to decade precipitation change from an average between 1900 and 2000. And so the solid black line is the observations, and the light gray lines are the prediction of individual climate models from various parts of the world for this historical period and into the future. And of course, there's a lot of natural variability, especially in precipitation. But if you look into the future in particular, although all of these models agree tolerably well with the historical climate record, they do start to diverge. They diverge somewhat in terms of temperature, but the big picture is that the temperature warms rapidly over this current century under this CO2 emissions scenario. But for precipitation, the models don't even agree about the sign of the change. There's a group of models which shows precipitation increasing. There's another group of models that shows precipitation decreasing. And although changes of 5 or 10% over a century may not seem like a much, because they add up, they can really affect the way our society works, our need to store water, for instance, and have water available for agriculture and cities and power and so on. So figuring out which of these scenarios is really the most likely for a given emission scenario is important. And this disagreement isn't just a feature of the Pacific Northwest. Many regions of the world show this kind of disagreement in regional precipitation change in particular. For instance, especially more regions that are more in the subtropics, like the Mediterranean or California and so on. Well, traditionally, we've attacked these problems using physically based models. So whether for weather modeling or for climate modeling, the way that these work is like in most other realms of fluid simulation. We have some kind of a complex real system with a whole range of scales. It could be a turbulent fluid of any kind, but the atmosphere has some additional wrinkles, such as, for instance, as cloud and precipitation processes, different kinds of surface topography and type, etc. And we then discretize the equations of motion or whatever other kinds of governing equations we can come up with for the different processes on the sphere. And then we use as fine a grid as a computer will allow and run them forward for a period of time. And for a climate model, we run that model forward typically for periods of decades to centuries or even millennia. But we still are basically trying to simulate the instantaneous state of the atmosphere throughout that period of time. So basically, we do climate as a form in the atmosphere of weather simulation. Of course, in climate, it's weather coupled to physical processes in other Earth system components like the ocean, the land, and the cryosphere. So we've had 60 years to make these models better and better, and they have become both better in terms of accuracy in the present climate and more sophisticated in terms of the processes represented. But nevertheless, we still have these fairly large uncertainties, for instance, in regional precipitation, or in fact, in the overall sensitivity of the amount of warming to the given amount of greenhouse gas. So you might ask, well, is there anything else we could do? In particular, is there anything we can do with machine learning now that we have all of these accessible tools and apparent ability to advance in a lot of different kind of science problems using this approach? So over the last 5 to 10 years, scientists have started to explore this more seriously. And in particular, some of the things we would like to do, as I mentioned before, are make these models more accurate, faster, and more affordable. And one of the reasons we think that this is possible is because a feature of machine learning, although it has issues for physical modeling, is that it's often possible to make machine learning algorithms that represent a system with fairly low systematic bias. And an issue with weather and climate models is they represent the processes well, but they often do have a tendency to drift away from reality a little bit. So that's what we mean then by systematic bias. So perhaps machine learning can address that problem to some extent. In addition, machine learning is optimized to run on GPUs, which are very fast and energy efficient. So in some sense, the code makes better use of the computers that we have. And also, weather and climate models, traditional weather and climate models are written in Fortran, which actually relatively few people learn how to use. Configuring them can be quite complicated. And using machine learning, we can actually potentially make replacements for those models, which not only would be more affordable, but actually also easier for a larger group of people to configure and run. So that's kind of the hope. Now, there's 3 strategies that people have used to try and use machine learning to better improve atmospheric models. One of them is, the simplest one is you just run the model and you try and use machine learning for bias correction. Now, this is actually a simple statistical technique. I think machine learning might over-describe most approaches for it, but is commonly already used in weather forecasting. Simple statistics can also be used for the process of what's called downscaling, taking coarse resolution output and then adapting it to finer resolution prediction. Another use of machine learning, which is a bit more sophisticated, is what we call hybrid machine learning, where machine learning replaces or corrects part of the atmospheric model. And we worked on that initially at Ai2. And another group at Google Research recently published work called the Neural GCM, which is, I think, the best embodiment of what this approach can do. So in their case, they learned the entire physical parameterizations, the part of the model that doesn't represent the fluid flow, and they replaced that using a machine learning approach that was trained on 50 years of past global atmospheric observations. The approach we'll take is actually the most complete approach, which is that you try to replace the entire atmospheric model by machine learning. So you're machine learning the evolution of the entire global atmospheric state. So in some sense, this is the most ambitious use of machine learning. It has the advantage in our problem that there's a lot of compensation between fluid dynamical processes and other physical processes in the climate. And with full model emulation, those processes are treated together, and so compensating errors aren't so much of a problem for accurate learning of the system. Well, going back to weather, which, as I said, a very related problem, there's been a huge amount of progress in the past 5 years on machine learning-based weather forecasts, such that they are now, in fact, better than our very best physically based weather prediction models, which is quite an achievement. So this started with work from the academic community, starting in the late 2010s, um, which showed the potential for this approach based on what we call reanalysis, which basically involves estimations of the three-dimensional state of the atmosphere every few hours based on the available observations. And then in the last couple of years, there are groups around the world that have demonstrated that you can actually produce better forecasts using this approach than traditional weather prediction models. And the graph on the right shows an example of this from one of these models called GraphCast. And so the plot shows the root mean squared error of the forecast as a function of the lead time of the forecast into the future. And so, for instance, if you look at any particular lead time, you can see that GraphCast has a lower forecast error than the HRES, which is the best physically based model. And basically, that reduction in error is equivalent to gaining almost a day in forecast skill at later times. Now we're having probabilistic versions of these models, which are potentially going to be even more accurate. So how is it that weather forecasts based on machine learning achieve this skill? Well, they all kind of work in the same way. So they are taking the global atmospheric state, which is at a minimum the sort of a set of grid points in three dimensions representing the temperature, the humidity of the atmosphere, and the wind components. And that represents, if you add over the entire atmosphere, millions of variables. And they're using that as input into an encoder, which encodes that into an optimal set of latent variables. And then that set of variables is worked on by two pieces of machine learning code, one of which is doing basically the fluid dynamics or horizontal exchange processes, and one of which is basically doing processes in each grid column, which represent most of the atmospheric physics. And those two modules talk to each other a number of times, again, with weights that are optimized during the machine learning training. The result is decoded to the physical state of the atmosphere 6 to 24 hours later, and then you run this model forward with those time steps of 6 to 24 hours. And a variety of approaches are used for this internal part, the decoder, the processor, and the decoder. Listed here: UNets, graph neural nets, neural operators, transformers, diffusion models, which are stochastic. The number of weights also ranges very broadly between published models. But as a group, these models train on 40 years of reanalysis, which is the most reliable estimate of global observations that we have in periods of a couple of days to weeks. So they're not really expensive to train. You can make a forecast very cheaply in a few seconds. And you get very large efficiency gains over using a conventional atmospheric model because you're taking a much longer time step and because you're using algorithms that are optimized to GPU computing. Now let's think about, well, okay, we know that physically based weather forecast models are the basis also of the atmospheric component of climate models. Well, what about if we use machine learning based weather forecast models and we try to run them forward for longer? Well, it turns out that that is generally not that successful. So for instance, we can look at this picture, which represents a few machine learning models run out for a period of a year. So what's shown here is 500 millibar height, which is a sort of a typical measure of the atmospheric state that's averaged around latitude. So it tends to be higher in the tropics, lower in the poles, and has a seasonal cycle. And the panel A shows what this should look like over the period of one particular year. And then forecasts for the same year are made with a couple of different models: Pangu, GraphCast, SFNO, DLWP, etc. And what you can see is that many of those models don't succeed in maintaining the seasonal cycle of the real climate at all. They work very well for 10 days, but they fall apart after that. So Pangu weather, if you try and make 3-hour forecast steps, it blows up. If you use 24-hour forecast steps, it makes a relatively poor climate. GraphCast doesn't work at all past 2 months. There are a couple of models. One of them is called SFNO, Spherical Fourier Neural Operator, which is put out by NVIDIA, which does produce a reasonable climate under some circumstances, but not terribly accurate. And another model called DLWP, which is put out at the University of Washington by Dale Duran's group, which also does a pretty good job. So that's potentially an issue. Well, okay, so what are some additional issues for trying to make emulators, machine learning code that would be good for climate modeling? Well, one of them is that all of the codes that I showed you are trained on historical observations, mainly from the last 40 years when we have satellites and these observations are reliable. The goal of climate models, on the other hand, is to predict past and future climates that may lie well outside this historical range. And we know that machine learning in general is not reliable for extrapolation because it's not grounded in physical principles which generalize past the training data set. So what our goal in my group has been is to not try to use the historical observations to train a climate model for these reasons, but instead try to train an emulator of an excellent physically based climate model. And of course, an emulator of a model can only be as good as that model is. So we're obviously not then hoping to make an emulator that's more accurate than that physically based climate model, but we still can speed it up a lot. So we can speed it up by a factor of 100 to thousands for routine simulations, for doing ensemble forecasting, for doing techniques like downscaling, which are routinely done with climate models and consume a lot of computer time. So that's sort of our initial goal. Now, there's a little bit more to this goal than it may sound here. So I'll talk a little bit about the vision of maybe how you can use this in ways that you might not yet be thinking. And so one of those ways that inspires me is that we could emulate climate models that we really can't afford to run as climate models in a physically based system. So for instance, we can make kilometer grid scale models of the atmosphere and of the ocean, but we can only afford to run them for periods of a year or a few years. So we can even couple those models together and run them for a few years, but we can't use this as a system for doing climate simulations that might be hundreds or thousands of years of computation. It's just too long, and we can't use them to do very large ensembles of runs. It's just too much computation involved. So what about if we take these models and we train machine learning to emulate the combination of these models and then use that in place of running this physically based system that we can't afford to run. So that's one of my visions for how we could use this in ways that might be more transformative in terms of the skill of climate models. Okay, so that's kind of what we're heading toward, and we're not there yet, but we are starting to make progress within my group, and I'd like to talk to you about that. So what we did first is we made an emulator of a simple system that's sort of basic to climate. So here, the simple system is that we assume we know the ocean, since we're trying to make an emulator of the atmosphere right now, and we just use a climatological seasonal cycle of the sea surface temperature, SST, and of other external forcings, sunlight on the top of the atmosphere. And we construct our emulator to predict the state of the atmosphere, the temperature, the moisture, and the winds at 8 different levels on a 1-degree latitude-longitude grid. I'll start with that problem, but I'll also show results where we sort of vary the external forcings from the present day to look at greenhouse warming a bit. So here the question is, can we achieve an emulator which not only is stable, but actually is accurate in terms of climate? What's a bit different than the weather emulators is the weather emulators treat the entire prediction problem as a forecast problem. So, they know the current ocean temperature and the current state of the atmosphere, but they have to predict everything. Here we're predicting the atmosphere, but we're forcing with the ocean still. So that's helping guide the atmosphere toward the right path. So with some of these models, in particular with models like SFNO, which are already pretty stable, hopefully then this is enough to make them perform well in terms of emulating the climate of the target physical model. Okay, so the training setup then is we use the humidity, winds, temperature, and surface pressure. We then use this methodology called SFNO from NVIDIA. And what SFNO does is it basically takes these fields, it translates them into spherical harmonics, and then it mixes up the fields in ways that are learned and optimal using something called spherical convolution. And then it mixes that then with a local column-based component to the prediction to make a prediction for 6 hours later. One difference of what we do from what most weather emulators do is we have, as do most climate models, a combination of different variables of different types. So we have prognostic variables, which are step forward on the 6-hour time step. We have forcings, which are external to the system. So in addition to sea surface temperature and insolation, we also, for instance, have surface type, land, ocean, sea ice, and elevation. And then we also have diagnostic variables. So these include things like precipitation, rain or snow, radiative fluxes at the surface and the top of the atmosphere, so we can compute things like energy balance, energy budgets. We can compute the energy balance of the land surface and so on. So our target model that we started with was from NOAA. It's basically a version of our national weather forecast model called the FE3GFS. And we saved 3-dimensional output from 100 years of a 1-degree simulation with this model. So that's actually quite a lot of data. And we used most of that data for training our model. Now, one way we reduce the data is that we only use 8 levels in our machine learning model. Physically based models tend to use many, many more levels, but machine learning model can represent all the correlations between what happens at different levels in a model much more efficiently than a physically based model can. And so you don't need as many vertical levels. Because we saved all the boundary fluxes and because of the way we computed our 8 levels as using sort of terrain following coordinates, we can actually calculate budgets, so mass, moisture, and energy budgets in each column. So that's actually important when you're trying to verify how well your model works as a climate model, where you expect it to conserve energy mass and moisture. And as I said, we've gone through various steps. I mentioned the annually repeating sea surface temperature forcing. We've also then gone on later, and I'll talk about those later, to more complicated forcing regimes, one involving historical sea surface temperatures and one involving connection to a very simple ocean model called a thermodynamic slab ocean model, and then varying the concentration of a greenhouse gas and seeing if the response of the emulator can be trained to match the response of the physically based model. Well, starting with just the imposed seasonal cycle of sea surface temperature, these were results that we obtained last year in 2023. After some working on our model, we were able to achieve a stable, accurate climate that basically matched the repeating seasonal cycle of the reference physically based model. So what's shown here is just the global mean temperature. T7 is the temperature in the lowest simulated layer of the atmosphere, which basically represents the lowest 1.5 kilometers or so of the atmosphere. And so you can see that has a seasonal cycle in the reference model. That's basically because the northern hemisphere has more land than the southern hemisphere. And so it warms up during the northern hemisphere summer more than the southern hemisphere cools. And you can see we are replicating that quite well. And there's no evidence of an instability. You can run this model more or less indefinitely and keeps doing the same thing. If you look at an integral measure of moisture, the so-called total water path, again, integrated around the globe, it also matches the reference model really well. And what's shown here is a period of 10 years of simulation. But as I said, you can carry these out for much longer. In addition, we can get a large speed up. We can run this model at 800 simulated years per day on one GPU, which is much, much faster. It's hundreds of times faster than the reference model. And here's an example of what the model does. This is in terms of a field that we care a lot about for climate, which is radiation. So this is the outgoing long-wave radiation from the top of the atmosphere for the first 100 days of simulation. And you don't expect that prediction and the target to match exactly because we're starting them from the same atmospheric state, but due to the chaotic nature of the atmosphere, the details of the forecast diverge, but you would like them to qualitatively look the same. And although if you stare carefully, you might see some differences. Basically, they're almost indistinguishable from each other, these two fields. So that's nice to see.
If I may interrupt for a second, is Pierre speaking? We have a question in the chat from Ananda Babu. I can read it for you, or maybe
yeah, that'd be good since I somehow hidden my chat.
The question is, are these results shown when the model was trained to predict just on one step ahead or more than that? And or did you have to train for differently for long rollouts?
No, with ACE version 1, we just trained with a single step. With a more recent version of ACE that I'll show you results from later, we actually trained for 2 steps, but that only improves the weather forecast skill. It actually doesn't improve the climate skill at all. It's actually quite remarkable that you can train purely on 6-hour forecasts and still get a actually quite accurate climate. But that is the case with our setup.
Yeah, maybe a follow-up question because I had a similar one. So for SFNO, did you have to do anything special for the stability, or just the fact of using a climate ocean is enough?
That was important. Also, we did have to worry about the variable normalization and the loss function.
Okay.
So yeah, but once we sorted those out in an appropriate way, then it worked more or less as originally coded.
Okay, thank you.
Now, I would mention, though, SFNO is really good for climate, apparently, but it's not actually the best weather prediction architecture, which is interesting. And I think that has to do with the fact that the spherical convolution assumption it makes is actually a bit too strict for our problem. And so as a result, I think it can't perfectly represent all three-dimensional interactions in the atmosphere. Okay, so just to show you then how we can do, we can look at a 10-year simulation using ACE, and we can compare it to a 10-year simulation using the reference model. And we see the picture in the middle. So in this case, what we're showing is precipitation. And you can see very little color. And so the idea is the biases are actually quite small. Biases are a small fraction of a millimeter per day. The pattern error is on the order of 0.47 millimeters per day. And you can compare that with different 10-year samples of the reference model compared with each other. So this is the natural 10-year variability of the model. And the bias is only twice as large as that natural variability, what we call the noise floor. By comparison, a 2 times coarser physics-based version of the same model has larger errors. So the emulator is actually very accurate in terms of climate. And in fact, outperforms a 2 times coarser version of the physics-based model on almost all of the output variables. In addition, without actually imposing humidity conservation, you come very close to getting it. So this is one particular 6-hour step, and there's a budget that humidity should, in a given grid column, should satisfy, which is that the tendency of humidity is due to a source from evaporation, a sink from precipitation, and then also a source from horizontal advection into the grid column. And we learn all of those terms individually, B, C, and D, and we can compare them with term A, which we also learn. And in the reference model, at this particular time, there's zero residual because it's a finite volume model that exactly conserves humidity. In the ML model, you get the situation on the bottom. The physics state is different, but you can again see that the balance of all of these terms is very, very close to zero, even though it's not zero. So why is ACE more stable than weather emulators? So architecture does make a difference. SFNO seems to be a very stable architecture for this. We just kind of happened on that by accident, but seems great. The normalization is important. I can talk about that more after the talk if anyone cares. And also, certainly, the specified sea surface temperature is anchoring the seasonal cycle and helping keep the model on the rails. What's shown on the bottom here is that we can do a 1,000-year simulation, and the end of that 1,000-year simulation, in this case for the global mean total water path, looks pretty much the same as at the beginning. So really, we can run this out for a very long period of time.
Thank you, Chris. There's a couple of questions maybe in the chat. So there was one, if I may, from Gian Giacomo Navarra. So have you checked how much your model results are sensitive to the input you give to the model, like excluding humidity from your input, and calculate the difference in model skill?
We've done a limited amount of that. I mean, for the atmosphere, we know that, that the temperature, the humidity, and the winds are critical fields. We couldn't even start to formulate a physics-based model without all of those fields. And so, for instance, humidity is critical to weather forecasts and climate because rain forms and then releases a lot of latent heat where it forms. And so that then affects the circulation. It feeds back on the circulation. So we didn't do that. Yeah, the kinds of ablations we've done, we've checked what happens if we use more or less atmospheric layers. I'll talk a little bit about conservation properties in a second. Yeah, we've done a limited number of ablations, but not surgery of the kind that was asked about there.
Okay, thank you. And then another question from Rosella Gigliardi. So as far as GHG, do you use cumulative emission or current emissions?
So we're using idealized scenarios where we specify the CO2 change. So we're not at this point trying to specify emissions, we're specifying concentrations.
Okay.
But none of the results I've shown so far use changed greenhouse gas concentrations. I'll talk about that in a second.
Okay, thank you.
Right. Okay, so one other question one might have about an emulator, which is trained on a lot of data, is how well it does with extreme events. And this is another kind of heartening feature of this emulator, is that if we take all of the grid columns on the globe over a period of 10 years and we make a histogram of the precipitation rate every 6 hours, no, every day, excuse me, at all those grid columns, and we compare the emulator to the physics-based model, which in this case we're emulating a different physics-based model, a DOE model, because it was a different paper. You can see that the emulator in green matches the histogram of the physics-based model in black pretty well, including all the way out to the tails, which are very extreme events, very strong precipitation that are actually also very rare. The scale in the vertical for the histogram is a log scale spanning 8 orders of magnitude. So we're able to capture extreme precipitation events, which is by no means guaranteed. Okay, well, so now let me talk about ACE2. I know I'm not going to have enough time to do this as well as I could at this point, but I'll try. So recently we've come up with a second version of this model that has a certain set of improvements and is trained on more sophisticated data sets. So one of them is that it has dry air and moisture conservation built into the machine learning. It has some architectural improvements, and it's also trained and tested on a data set which includes the full range of historical sea surface temperature variability between 1940 and 2020. So that includes both the effects of greenhouse warming on ocean temperatures and also variability like El Nino, which are sort of year-to-year variability in ocean temperatures. So this is a more rich data set which you can both train the model on and compare it with. Because now you can see whether the emulator is able to reproduce the trends and also whether it's able to reproduce the atmospheric force response to things like El Nino. So I'm going to actually skip a couple of these slides because I know we're going to end up running out of time. So let me just talk about what we use for training. So in this case, we actually decided, okay, well, since we're here trying to match historical data, let's try and train on historical data, namely reanalysis from 1940 to the present. So what's shown here is in the light green is ACE trained on the reanalysis, ERA5, in the solid colors, and ERA5 is the dashed colors. And there are 3 realizations of ACE shown here, started with a different initial conditions. And the picture is such that you probably can't see which is ERA5 and which one is ACE, because you can't tell the dashed and solid lines. But that's good, because it means the emulator is representing the global mean temperature at 2 meters in this case very well. Now, of course, over 70% of the world, the atmosphere is the surface is ocean and the sea surface temperature is specified. So you might think, well, no great shakes, but there's still a lot of land and in particular high latitude land where there's plenty of opportunities for this to go wrong. Same is true for total water path. this compares with a previous version of our model in purple, which is not able to represent the trend in total water path. We didn't have data for the 2-meter temperature. And if you instead train the model on a different model, the same model that we had before, this NOAA model, it in fact has a different mean climate, even though the same sea surface temperature is specified. It's different from the observations. But again, the emulator in solid is able to track the dashed lines, the sort of turquoise blue lines, which are the original model. So basically, again, the emulator is able to represent not only the means, but the interannual variability and the trends very well in this data set. And again, I'll just show you this picture, which just shows the regression of the precipitation predicted by either a data set on the bottom, ERA5, or the SHIELD model. The regression on a measure of El Nino called Nino 3.4, which is the temperature in the central equatorial Pacific, the sea surface temperature. And so you would like the emulator to match the pattern of its trained data set. So for instance, A should match D. And in fact, it does. So the interpretation of this plot is that there's when we have an El Nino, when it's warmer in the central and east Pacific, you get more rainfall over the east and central Pacific and less over the Indonesian region. And you can see that ACE2 ERA5, for instance, matches ERA5 almost perfectly. So that's nice. If you just try this with our emulator trained on climatological SST, it also gets the same pattern, but it's too weak. Okay, fine. So one last thing then I'd like to talk about here is coupled to a simple ocean. So far, we don't have an ocean emulator that we can use that's sort of industrial strength that emulates the entire three-dimensional structure of the ocean well and works on decadal timescales. But we can use a simplified ocean model to learn some things about how well we could emulate climate change with this model. So we use what's called a slab ocean model. Basically, a slab ocean model takes the heat that comes into the surface of the ocean and uses it to either warm up or, if there's a heat loss, cool down the ocean. It also has a horizontal heat flux, which is assumed to be independent of greenhouse gas and depends only on the season and location, which helps it match the current day climate with current day concentrations of CO2. So what we can do is it's very easy to code a physics-based atmosphere model to have a slab ocean coupled to it. And it turns out it's very easy in PyTorch to code up a slab ocean, which does exactly the same thing. So we can have the whole system in machine learning. So then what we do is we generate training data set from our physics-based atmosphere plus slab ocean model from 3 50-year simulations, one with present-day CO2, one with doubled CO2, one with quadrupled CO2. And then we train our emulator on a mixture of those simulations using CO2 as one of the input features. And we see how well we can replicate the temperature and precipitation patterns that come out of those physics-based simulations using the emulator. And again, the emulator works really well. So it works well in sample. In other words, if we try to do long climate simulations in the 3 climates we trained it on, and this isn't guaranteed because we're training entirely based on 6-hour tendencies, but it also works out of sample 3 times CO2. So here again, the comparison between the blue and the black lines basically indicates a good comparison on this global mean surface temperature. And in fact, it's also good at predicting the climate change pattern. So between present-day CO2 surface temperature and 3 times CO2 surface temperature, which is an out-of-sample test. So you can see, again, the target model is shown on the left. So there's a temperature increase due to the higher CO2 concentrations. It's larger over land than it is over ocean. It has a pattern over the ocean that is basically due to feedbacks between the surface energy flux in the ocean. And you couldn't tell the difference between Ai2, the emulator, and the physics-based model on the left. On the other hand, if you take a coarser resolution version of the physics model and you use it to do the same test, you can see the difference more. That's the plot on the right. And in fact, there's a larger error in emulating what the model, the 100-kilometer physics-based model does from the 400-kilometer model than there is using our emulator. So the emulator is actually better, again, than a coarse resolution version of the same model in this climate change case too. There are some other examples I could get back to, but in the interest of having time for questions, I'll just summarize here. So basically, we don't yet have an emulator that's suitable for climate prediction because it's not coupled to a full dynamical ocean, but it's nearing that. I think it shows that that is feasible, probably going to be feasible in the near future. We can faithfully reproduce a reference model's climate in a variety of configurations, including ones that are sort of approaching relevance for climate, namely historical climate and slab ocean as an example of a ocean-coupled configuration. And it's able to capture, in the historical climate case, the correct forced response to greenhouse gases and to El Nino. The emulator in all of these cases is very cheap and easy to set up and run, much cheaper and easier than the reference model itself. And right now we're working with a group at GFDL and NYU on coupling this emulator to a dynamical ocean model. We have all of the code and data available on a GitHub site that some people are starting to explore for academic purposes. So that's it. Thanks.
Yeah, thank you very much, Chris, for the great presentation. And thank you, everybody, for attending, even though some of you is pretty late or very early. So I'll just go ahead. There were a couple of questions that were asked during the presentation, but I'll let you go, Chris, so that you could finish on time. So Paul Leopardi has a question that says, could you train the same ML model against each of the model outputs in SIMP P6 to obtain an heterogeneous ensemble?
You could if you had the data to do that. Unfortunately, the CMIP6 models don't have 6-hourly, 3-dimensional fields of all the things that we need, but there's no problem with doing that. Our experience with training E3SM, a DOE model with exactly the same emulator training workflow as we did with the NOAA model, was we didn't have to change anything about the training protocol. So yeah, so we could do this, and in fact, that would be a sort of an interesting thing to do. I think it would be a more interesting thing to do when we had a coupled version of the emulator and we could sort of train against different coupled models, because really in the end, CMIP6, if you think about what the acronym is, it's Coupled Model and Comparison Project. We know the atmosphere-ocean coupling is crucial for climate. So, but in fact, in about 30 seconds, I'll have to dive off to another meeting where we're going to talk about doing a machine learning into comparison that's aimed toward different groups trying to do exactly that problem.
So another question, so from Araldo Velio, so if climate change is driven up to another climate atmospheric equilibrium, would it be more appropriate to apply unsupervised ML approaches than supervised ones? And is there someone in your group that is working on that?
Well, that's a great question. And of course, if we had some idea about how to apply unsupervised ML to produce a more robust ML-based climate modeling, we'd go for it. But at this point, it's still sort of unclear how to do that, or in general, how to blend ML with physics-based reasoning so that it generalizes better to the future without having to rely on an external model for training. That's a bigger challenge. That's sort of maybe the big challenge of the next decade.
Thank you. Then we have two other questions, at least from the chat again. And then if others have questions, you can ask. So do you want to ask your question, Mohammed, or do I read it?
I can see it. I'll
Oh, you
address
can
it.
see it.
This is
Okay,
about the
okay. Go ahead then.
simplicity of the slab ocean. Yeah,
Yeah.
okay. This is certainly true. The slab ocean was simply a crutch for how can we look at the climate change response of our emulator in a way that is at least somewhat useful for telling how well it could represent climate change response. And I should say, earlier on in the history of climate modeling, slab ocean models were in fact widely used for this task of assessing climate sensitivity of different physically based climate models. So this does have a precedent, but from our point of view, it's simply something we could easily code in machine learning and compare to a physics model and therefore use to test our overall strategy.